Right. All right. Well, that was a struggle. Uh, Zoom was extremely slow. I don't know what's going on here, whether it doesn't like my computer or what. Okay. Good morning. It's 27th of July. This is the Cosmology Discussion Group meeting. Welcome, everybody. I'm going to talk about fixing Einstein's math again today. Um, I think Vladimir has got um, talk for next week. Is that correct?
Yes, I will.
And so anybody else that wants to give a presentation on a topic, let me know. Um, okay, so I'm going to get started here. Let's go. Okay, I got the right. Can people see this here?
No.
My computer's running slow, so. All right, well, good morning. I'm going to continue my discussion about fixing Einstein's mistakes. Um, I think there's been a lot of talk about his metaphysical mistakes. I'm talking about math mistakes, and it turns out there's many math mistakes. So I'm gonna go over again today some of the fundamental ideas. I'm going to try to recapitulate the main ideas of measurement and measure scales, and to further elaborate on the basic principles of what this mathematical method is. Okay. And all right. So the first thing that we have to understand is I've talked about the basis transformation. What is the basis transformation do? Something's not right here. You see the presentation?
Yes.
Yeah.
I've lost the video for you guys, so I don't know what happened. All right. The basis transformation laws are reciprocal and are used to define the measure units and the relatively moving frames S and S prime. So what we have is in the theory, we have ideal frames of reference with coordinates, but we don't have the coordinates marked out yet. How are we going to mark the coordinates? Well, what Einstein does is he just picks some coordinates and says that they're the same in both frames, but we'll find out that's not necessarily the case. So the first thing that we have to do is we have to mark what are where the units are going to be on our frames of reference. So this is what the basis transformation does. I'm going to explain. The frame S is called the rest frame, and then in this theory, it's a preferred or stationary frame, and in which we define the standards of measure such as the SI unit. So in the frame that's at rest, we can use SI units. You know, the SI units, those are the standard international units. They're agreed to by international treaty, and they're the units that are used in doing scientific measurement all around the world. So those are well-defined objects. According to measurement theory, okay, and this is where Einstein doesn't really, his theory isn't really based on measurement theory. It's kind of an ideological theory. That's why it's said to be metaphysical. According to measurement theory, a measurement consists of a measure unit and a number representing the number of measure units recorded by the measurement. I don't think people really understand that. I use the example of a ruler. I'm going to show a ruler here. I can't see me. I don't know why I can't see me. Can you see my ruler here?
Yeah.
And you'll notice that the ruler has marks on it. This is a standard thing. It's got like 1 inches, 2 inches, 3 inches, 4 inches, 5 inches, 6 inches. Now the inch, the unit inch, that's the unit. So that's the measure unit. And then the numbers on the scale are the what they call the coordinates of measure. Okay, so when I say an object is 6 inches long, it's 6 of these 1 inch units. Okay. All right. Okay. Oh. Okay, now the basic transformation laws. What the basic transformation law is, I'm going to use that to lay out the points on the ruler. Okay, and a measure unit is defined. Okay, in the rest frame we talked about, it's defined in the SI units, and so we'll use. I've got this ruler has got centimeters on it, so that would be SI units, although the SI units are meters. A centimeter is 1/100th of a meter, so we could use centimeters and use that to lay out our ruler. So we know what the units are in the rest frame. They're the SI units. All right. Okay. So how do we lay out these units on our ruler? So what we have is we have a ruler with units on it for the rest frame, and then we want to lay out units for the moving frame. Okay, so the moving frame units are not the same as the rest frame units. Now, Einstein assumes and relativity assumes they're the same. There's no reason why he did that. That's just an arbitrary assumption that he assumed. So that's part of his metaphysical assumptions. Okay, so we have this basis law, x prime equals beta x. Okay, and we have units in the rest frame. And so what we do is we mark out a measure unit 1, beta units measured on the stationary frame scale. So we mark a 1. So the 1 on the moving frame scale is marked at beta on the S scale. And then we can use the law again, x prime equals beta x. And for the second unit on the rest frame scale, we get that the unit on the moving frame scale is 2 beta. So it's 2 beta on the distance on the rest frame scale, and we put a mark 2 there. Mark 2, it represents units on the moving frame. And we can do this marks for all the marks on our ruler. What's your question?
What is beta, please?
Beta is the Lorentz factor.
It's more commonly called gamma now, but anyway.
Yeah, I use beta because Einstein used beta. I've explained this too many times. Yes, the Lorentz factor. Okay.
Why would you use such a factor, gamma or beta, in the first place?
Because the theory requires it.
The theory. Oh my goodness. Okay. That's sort of a non-answer.
Just trying to throw monkey wrenches into the talk, Jim.
Sorry, don't mean to do that. But the theory says it is not really an answer. So we'll just record there is no answer to that question at the moment. Proceed.
Okay. We lay out, now we can do the opposite for the other we can start on the moving frame and we can lay out units on the moving frame and we can find units in the rest frame. And when we find the units on the rest frame, they're related to the units in the moving frame by dividing by beta, which is the Lorentz factor. And we have the law x equals x prime divided by beta, which says that units in the rest frame, okay, are found by dividing units in the moving frame by the Lorentz factor. Okay. And so we can do this again. We take the unit in the moving frame, we take a 1, and we divide that by beta, and that tells us where we can put the first mark on the rest frame. And then we can do that for all the other units that we mark on our scale. Okay. Now, does anybody have any questions about this? This is pretty straightforward stuff.
Well, couldn't the moving frame and the rest frame be interchangeable? I mean, you know, couldn't you observe from the moving frame and that the same effects would occur considering what's the rest frame is moving if the moving frame were at rest?
I'm not sure what your question is.
I mean, couldn't you choose any rest frame? Like you could decide, well, this here's the rest frame and this is a moving frame, but it could go the other way as well. Like if you wanted to measure from a moving frame, the rest frame would be moving relative to that.
You're confused by relativity, I think.
Well,
Right now we're just talking about
what is the rest frame? There isn't one fundamental rest frame. I mean, can't you choose many?
Now you're talking metaphysics.
Can't you choose more than one rest frame though?
Yeah, you could possibly. I'm not even talking about the metaphysics. I'm just talking about how we're going to set up, how we're going to do the measurement.
All right.
You understand that?
Well, when the units of measurement transform, like the faster that you go relative to another object, the distances get shorter though, right? Like the faster that you go.
Not necessarily. We'll see later that that's not necessarily the case. The whole point of this discussion is that what happens is that when you're moving fast, you're measuring in a different scale of measurement. Do you understand that?
Well, I mean, I have many questions about it.
Well, you have to sort of understand that's the basic principle that we're talking about here. As I said, Einstein assumed that the scales were the same. The rest frame scale, the units that are marked on the rest frame scale are the same units that are marked on the moving frame scale. So if you put one next to the other, which is what I've discussed here and how we're doing that, we're putting one scale next to the other scale, and we have a relation that tells you how to mark the units on the different scales when they're at rest relative to each other, sitting next to each other. Okay, now Einstein says the marks on the two different scales are the same. And he says that both for distance and for time. Okay, I'm saying that's a mistake. All right. Do you understand that part?
Who, me? Oh, well, I have to admit, I don't understand the technical math. However, though, I understand the concept.
Well, do you understand the concept that it's not necessarily the case that the measure units are the same for the moving frame and the rest frame?
Well, okay. It was my understanding that the faster that you go relative to another object or a light source or whatever, that the units of measurement shrink. Well, that's your view, actually. Actually, Lorentz and Einstein thought that the objects actually shorten in length. But, I mean, why wouldn't that apply, though, with the theory?
Well, I'll discuss that later. That has to do with the assumption that the measure units are the same. And then when you do this calculation using the Lorentz transform, okay, they select a solution to the Lorentz transform that gives them a contraction effect. So in other words, they get that the object has shrunk, okay, but that's only because they used they picked mathematics that gave them that answer. That help
What
you
would you say?
understand?
What would you say causes the units of measurement to transform?
The physics that they're discussing. So we know that the physics at rest, the physical laws don't apply to when you're moving very fast. Okay, now I'm going to talk about how these transformations come about. And if you've been paying attention to the previous lecture on time, on the transformation of time, you would notice that Einstein has this, he puts in these different, into the Lorentz transformation formula, he puts in criteria. In 1905, he put in x equals vt and solved the equation. And then in later papers, he used the inverse Lorentz transform and put in the criteria x equals 0 or x prime equals 0 in the rest frame coordinates. And I've given this a name, what he does, I'm calling it evaluation. Okay, and it's like solving an equation. Okay, so you have an equation, you put in a value into one of the variables in the equation, and then you solve it under the condition of that variable. And so what happens is that you have two conditions of evaluation. And you have a Lorentz transform and you have an inverse Lorentz transform. And we're going to solve these equations when the origins of the coordinates coincide. So that means now we can try to figure out how the marks, where I was talking about previously, how do we determine how the marks, the units of measure, the marks on the scales, how do they relate to each other? And that's what we're going to do here. And this is done by specifying the conditions x equals 0 for time. That's in the rest frame. X prime equals 0. That's also for time in the moving frame. And then to do length, we specify the condition t equals 0 in the rest frame, and then t prime equals 0 in the moving frame. Now, we don't know what we're going to get when we do this, but this is how it works. I'm the first person that did this. So what I did was I took the Lorentz transformations. There's equation 1 is the Lorentz transformation for distance. Then we take the Lorentz transformation for time in equation 2. Then we take the inverse Lorentz transformation for distance in equation 3. And then the inverse Lorentz transformation for time in equation 4. And we put x equals 0 into these equations, and we get equation 2, we get the basis law, t prime equals beta factor t. That's the basis law.
When supper was ended, he took the chalice.
Please turn off your audio.
He gave it to his disciples.
Okay, then in equation 3, we solve this equation and we get x prime equals minus vt.
The blood of the new and eternal covenant,
Cornelius.
which will be poured out for you and for many, for the forgiveness of sins.
Hey.
Do this in memory of me.
All right, so then now we have equation 3, which is an intermediate equation. We get x prime equals minus vt. Now we substitute that into equation 4, and when we do that, we get I don't know.
It must be
So-
Cornelis.
I'm not sure. I don't know how to mute him.
There we go.
Okay. That was not very pleasant. Okay, so equation 4 we get by substituting the result of equation 3 into equation 4, and we get
My button just accidentally came on.
basis law.
That's
Please turn off your audio, Cornelius. Please mute your audio.
I was explaining that the button just accidentally came on. Forgive me.
Well, please mute it.
Thanks, Cornelius.
Okay, so, all right. Now, this is really kind of the important point here is this step of taking equation 3. When we solve equation 3 for x equals 0, this is in the rest frame evaluation, we get x prime equals minus vt. And this is kind of the trick, okay, that you have to know in order to solve these equations. We substitute that into equation 4, and that gives us the solution t equals t prime over b, and that's the important thing. All right, so we get from this procedure, we get equation 2, which is the basis law equation, and we get equation 4, which is the inverse basis law equation. Okay, and so what is interesting about this procedure is that x equals 0, the evaluation procedure for x equals 0 gives basis change laws for, in this case, distance. Okay, now if we do the x equals 0, which is evaluation in the moving frame, we can do the same thing. Now notice here in equation 5, we say x prime, we solve this equation. This is the equation 5 is the Lorentz transform for distance. Set that equal to 0 and solve for x equals vt. Okay, this is what Einstein did in his 1905 paper. But he just said, let's just take x equal vt, and then we'll substitute x equal vt into equation 6. And no, yeah, I think that's equation 6. Okay, we substitute that into it, and then we get a transformation law. We get a basis coordinate transformation laws. Okay, that's the trick here. This x equal vt is a solution for x prime equals 0, and so that's what that means. X equals vt is essentially equivalent to saying that x prime equals 0. So it's a in the moving frame. And so what happens is now in these equations we get coordinate transformations from these equations. Okay, I'm going to move on here because we're getting and then we can do the similar procedure for t equals 0. Okay, and now we're evaluating again in the rest frame. We're doing an evaluation procedure in the rest frame at t equals 0, and then we get these basis laws for distance. And equation 9, we get the basis law. And then equation 11, we get the inverse basis law. And we can, and we do that by, now this is an interesting thing here. Equation 12, we solve this, and then we get this substitution equation that we can put into equation 11. Okay, and then that's how we solve it. So kind of the trick in this evaluation is that you solve one of the Lorentz transformations and get a result, and then you substitute that into another equation to get the result. And this is kind of interesting that the mathematics works out this way. All right. Then we can do the same thing here for t equals 0. Okay, and we get coordinate transformation loss. Okay, so I'm not going to go into the details, but we have the same situation again, where we have an equation 14. We solve it for t prime equals 0, and we get an equation that we can substitute into equation 13. Okay, and that's how we get this complete set of equations. We'll use this little mathematical trick. All right, so what that is tells us is that we can use this procedure consistently, this evaluation procedure, and we can get all the 4 rules. Actually, there are 8. There are 4 of them for distance and 4 of them for time. Okay, now if we go by what Einstein says, we only have 2. Okay, and if we go by what Solari says, we only have 2 as well. So that's kind of a problem, because this method here is saying if we use Einstein's method, it's based on Einstein's method, okay, which he initiated in his 1905 paper, although it's very unclear what he was doing. And if we extend this method and do it in a complete manner, we get 4 solutions for time, and we get 4 solutions for space. And Einstein doesn't get 4 solutions. Okay, he only gets 2. Now, it turns out that if we use those solutions that Einstein gets, let's see, they're down here. All right. Okay, so what happens if we use Einstein's 2 evaluation conditions? Well, we get these paradoxical results. Okay, and that's really where all the paradoxes come from in special relativity, because he's using he's coming up with 2 evaluation conditions, and there are no solutions there are no mutual solutions for those 2 equations. So the paradoxical solutions resulting from special relativity, asserting that the symbols are all the same in the preceding equation. So I didn't make any distinctions between the symbols in those equations, because Einstein didn't do it. And that's sort of what leads to the problem. You don't really, according to his theory, because he doesn't treat these, he doesn't understand there's really a difference between the Lorentz transform and the inverse Lorentz transform. He thinks that the inverse Lorentz transform, all you do is just exchange the symbols. You take the prime symbols and the unprimed symbols, and you take the prime symbol away in the one equation and so we take the x prime away in the one equation and we put x prime in the inverse equation. Okay, and so you're just exchanging the symbols, and that doesn't really he doesn't take into account that maybe when you do this, the symbols don't mean the same anymore. Okay, and so when you do that, what you have is paradoxes. And we all should be familiar with paradoxes. There's the twin paradox, which is the famous paradox. There's paradoxes relating to distance as well. Okay. So the paradoxical solutions resulting from special relativity asserting the symbols are all the same in the preceding equations is resolved by recognizing that the equations are solutions of the evaluation condition x and t equals 0, and their basis transforms. And then we have solutions for x prime, t prime equals 0, or coordinate transformations. Okay, and that has to do with the fact that the inverse Lorentz transformation is not, that's not really a correct definition of what it is. It's more properly called the dual transform or the adjoint transform, because it's not really the inverse transformation, because its symbols don't have the same meaning as the Lorentz transformation. So we can call this we really should be calling what Einstein calls the the inverse transformation should be really called the dual or the adjoint. And so that assumption is what leads us into problems and special relativity. Okay, I'm going to try to end up here. Basis laws allow us to set up the coordinate system of axis for the S and the S prime axes having different scales arise from the setting the condition X and T equals 0 in the evaluation condition. So if we set X equals 0, X and T equals 0 in the equations for the S frame, the S coordinate frame, we get basis laws. Okay. If we do the X prime, T prime equals 0 in the moving frame, we get coordinate laws. Okay. So that means that the paradoxes go away because the symbols no longer mean the same thing. So the symbols in the basis transformation don't really have the same meaning as in the coordinate transformation. And so we'll go back to what we said earlier about measurement. The basis laws change the measure units, okay? And the coordinate laws change the number of measure units that are in a measured time or distance. So when we report a measurement, say 6 inches, we have 6 measure units called inches. If we do time, we say we have 10 seconds, we have 10 measure units called seconds. And that's why these are different, because we have to specify what the unit is and how many of the units are being counted. Okay. Okay, so then we use that evaluation procedure, okay, that I just talked about. That gives us what the basis change laws are. So then but the basis laws to tell you how the marks are set up on the ruler, the marks on the for the S frame are not the same as the marks for the moving frame. Okay. And so that tells us that the measure units or how we're doing measurements in these two different frames are not being done in the same units. Okay. All right. That kind of ends it here. Here's kind of an example of this. An example is the muon decay. I think I've got a few minutes here. I'll talk about the muon decay example. This is pretty famous. This was not predicted by special relativity, but we know that cosmic rays coming in, they can reach the ground, and they're not supposed to, because these muons are supposed to decay pretty quickly. And how do they reach the ground? Well, it turns out that the time unit of the muon is changed by when it's moving fast and when it's not moving fast. Okay, so we can say that the time that it takes to decay when it's moving, not moving, or moving very slowly, we can say that's time t, and then we can use the basis transformation law, t prime equals beta t, which is the equation number 2 from the evaluation conditions. And from that, we can calculate the moving frame decay time. Okay, so this is an example of how the basis law can be used. Now, it turns out they do these measurements, and it turns out that this equation, t equals beta t, works pretty good, okay, for predicting the muon decay time. All right, we got about 4 minutes here. Anybody have any questions? All right, well, thank
Well,
you.
well, how is how is the beta decay, the length of the lifetime of a muon particle extended? How is that accounted for?
So you want to know what the metaphysics is?
I guess.
Well, the theory doesn't say what the metaphysics is. The theory basically says that we can account for we have a law, which is the basis transformation law, T prime equals beta T, that we can apply this law, which is derived from derived from the Lorentz transform under the condition that x equals 0. So we're doing evaluation in the rest frame. So this tells me that in terms of the rest frame units of time, the time that the lifetime of the muon is longer when it's moving fast than when it's moving slow. And if we're to believe the experimentalists who have done lots of experiments on this, that this law, T prime equals beta T, describes the phenomenon fairly well, although they use statistical samples and there's some variation in that. Does that make sense to you?
Yeah. Well, the phenomenon seems to suggest time dilation, even though I don't agree with it. I mean, I can see why people might make that conclusion. There might be some other explanation of which we're unaware. However, though, I don't see how I don't see how it could be taken into account another way, because I mean, I don't think it's known why beta particles have extended lifetime when they travel fast.
Well, according to the theory, the Lorentz transform describes the phenomenon correctly. And you threw in a bunch of stuff like time dilation. That's special relativity talk. Okay. Now it turns out that Einstein wouldn't describe it this way. That's one of the problems with his theory. You have to have a very, very convoluted explanation of how this works in terms of special relativity. In terms of my discussion of my explanation of it, the only thing I need to know is that the law T prime equals beta T, it fits the experimental data. Okay, and I don't say there's any such thing as time dilation or anything else like that. According, my explanation is that you have two different scales of measure. You have a scale of measure for when the muon is at rest. So you measure its time at rest, okay, in one scale of measure, and then you have the muon's time to decay in motion, and it's beta times longer. So if we say that the decay time is a unit or a time measure unit, then we say that 1 unit of beta time when it's moving is longer than a unit of decay time when it's at rest.
One of the problems with this explanation for the muon decay, I mean, in conventional theory, I suppose as well as your explanation of it, Harry, is that if you're looking at it from the point of view of the muon and its clock, whether the units change or whatever, say in conventional terms, they say, well, it slows down, but also there is length contraction, or maybe in your exposition, the units become larger, and I think those would cancel out actually if you look at them.
What would cancel out?
So let's look at it in just terms of conventional. Yes, I'm always a bit paranoid that the powers that be are cutting one off, because actually I was raising some very fundamental point about the conventional view. I'd have to think a little more about your own idea about changing units, but looking at it from the conventional point of view, I think they would say that why can the muon last so long to get to the Earth's surface? Well, they say, looking at it from the point of view of the muon's clock, it's slowing down. So it's not going to disintegrate so rapidly. It's going to remain. But
Let me
using
stop you. Muon's not really a clock, but what they're saying is that there's a time measure unit in the muon. So they're saying that there's some measure unit of time that exists, and that's equal to the decay time of the muon, right?
Yeah, I'm using it a bit. I'm personalizing the muon as if it were a person. But yes, that's essentially the case. But what they don't say also is that from the conventional Lorentz transforms, as envisaged in SRT, admittedly, there would also be length contraction. So from the muon's point of view, let's not call it clock for the moment. From the muon's point of view, it has to traverse a lesser distance to get from the outer atmosphere to the Earth's surface. So therefore it would decay, or in fact the two effects would cancel out.
Yeah, well, it turns out, I know what you're referring to. That's a misuse of Lorentz contraction. And it turns out that's just a math mistake. It's another math mistake that Einstein made, which I'm going to talk about now. But that's a good segue into Lorentz contraction. And they get messed up because they say that the Lorentz contraction makes the distance that the muon has to travel less, which doesn't make any sense.
And they're assuming that it's the same muons. What about the muons that are that people are building detectors deep down in the Earth to detect muons, because muons have a property of being able to penetrate.
You're talking about neutrinos.
No, I'm talking about muons. And muons are penetrate material, according to many authorities, just as well as almost as well as neutrinos do. And so all of this is based upon the assumption that it's the same muon, an assumption for which there is no evidence at all, none.
Well, you're disputing. You're making a dispute about the claim, whether or not the muon claim is true or not. I'm accepting it for the purpose of this illustration, so I'm not really sure that's relevant. Yeah, you can argue about every experiment, whether it's valid or not, and give arguments that it's not.
Or whether it's even the same muons that are detected in the atmosphere, at the surface of the Earth, and at great depths.
They use an ensemble of
in other words, without the assumption that it's the same muon, and you're talking about two populations of muons, those detected in the atmosphere and at the surface of the Earth. But there's that third population that are detectable in the depths of the Earth. The assumption that all of those are the same set of muons is without any basis whatsoever. In other words, there's no need for...
I have no idea what you're talking about, and I think it's kind of not really within the scope of our discussion.
Well, it's sort of my understanding that that physicists...
I shouldn't have brought up this as an example. I see now. Because anytime you talk about... go ahead.
I'm sorry. I mean, I'd always thought that physicists can follow muons, like they can detect them and follow their course down to the Earth. I don't see how they could possibly do that. But
as I mentioned before, they take an ensemble. They take they make a measurement over a period of time, and they measure an ensemble of results.
Oh, if it's a burst of them, your burst of one is only going to happen at one particular time. So if you see that burst coming, then you measure it in both places. You're going to have something identifying that it's the same grouping at least.
So it's based on an ensemble, and they take the average. What they call the decay lifetime is really an average.
How they measure the speed of them? Because in your Lorentz parameter, it must be v, speed. How they measured it?
Well, I've been down this road before, and they have, when they do these measurements in accelerator machines, they can make measurements using their scintillation detectors of how fast it's moving because it passes 2 points. And I have to admit, Bob, I'm sure you remember we had this discussion where we sent a message. We sent an inquiry to this guy who, Don Lincoln, isn't that his name?
Yeah.
We sent a message to Don Lincoln actually asking exactly that question that you asked, Vladimir. Okay.
Yes.
And he claimed to be, he's got a video where he talks about doing these decay experiments. So we sent him a message and asked him exactly that question, and we got no real clear answer.
Well, I cannot believe in any result if there is no measurement procedure.
Well, there's you can, I think I dug up some of the, if you really want to dig into this, the problem is when you say, show me the measurements, they'll send you an inch thick report, which tells you everything that you don't really want to know about. Tells you how they calibrated every ancillary piece of equipment, but doesn't really explain the experiment very well. So,
unfortunately, nowadays, they're so convinced of this that, yes, they may have initially measured with scintillation counters or other theories, but now they're so sure of this that they actually say that the lifetime is decayed by this factor, gamma factor or beta factor, as you call it, and they plug that back and they say, therefore the speed must be such and such. So it's really a circular argument.
Well, not exactly. It's pretty clear that they are measuring that the time of decay is longer when the muon is moving faster than when it's at rest. Those experiments are pretty clear at demonstrating that result. Okay. The problem that you run into when you're dealing with this is their explanation in terms of Einstein's theory of relativity is very unclear because he doesn't have a basis law in his theory. Okay. He's got a coordinate law, and they have to do some mathematical gymnastics to make it make sense. And then you also have where they claim length contraction. There's a problem with that because then they have to, do some hocus pocus explanation to explain things away. So it's not really it's really not well consistent with special relativity.
Harry,
you want to say something?
From my point of view, I think they use the calorimeter, which is i.e. they measure the impact energy of the muon, and that infers the mass from the increase of mass, and then you can work back to the speed.
Well, they do an energy calculation. They say that because the energy of the beam is x, therefore its velocity is such and such.
Yes,
that's But when you try to, as I said in the example that we did, where we tried to, do they actually make a velocity measurement of having it go past 2 points?
No.
I don't think they actually, it's not clear whether they do that or not.
They don't do that anymore.
Does that answer your question, Vladimir? All right. I'm going to proceed on here to talk about length contraction mistake. And I think length contraction is a mistake. Okay. And my theory, anyway, I'm going to talk about how Einstein came up with this idea, used to calculate length contraction. And then I don't think there's any such thing as length contraction. I don't think it exists. And we'll talk about that. Okay, and a good example of this is in the muon decay experiment. They have to make the assumption that the distance from the atmosphere where it hits the atmosphere and turns into a muon and the Earth is contracted. And if you've ever read that explanation, it doesn't really make a lot of sense to you. So they're kind of in a problem. Okay, so in 1905, Einstein's 1905, he starts in the moving frame and defines the Lorentz transformation. And he defines a sphere in the moving frame. And then he goes backwards into the rest frame using the Lorentz transform for length in the rest frame, transformed into the moving frame, solved at t equals 0. Okay, so here's the t equals 0 solution. All right, so that means it's a basis transformation in my terminology. X prime equals beta x, and you would think that shows that the distance in the moving frame is elongated or dilated. But no, what he does is he just flips this equation, this x prime equals beta x. He flips that upside down and says x equals beta x prime divided by beta, and he concludes that the sphere is contracted in the moving frame. Okay. So this is kind of kinky in my opinion. Okay, in 1907, he kind of revises things. He defines the body at rest in the moving frame S prime. Notice things are defined by Einstein in the moving frame. And then he kind of goes backwards. This is why I've said that he does things backwards. It's kind of confusing. All right, so he defines a body at rest in the moving frame S prime with coordinates x and x prime, where the prime is the moving frame. So x prime means the moving frame. Then he uses the Lorentz transform. He doesn't use the inverse Lorentz transform. Whereas for time, he uses the inverse Lorentz transform, but for distance, he uses the Lorentz transform. This is kind of like a little sleight of hand on his part. He's not really doing things consistently. He's not talking about time and distance in a consistent way. He's using different methods to demonstrate time dilation and length contraction. Okay, and so what he does is he uses the Lorentz transform, and then he doesn't actually tell us that he's setting t equals 0. He says there is a coordinate relation that holds for all times. It's kind of flaky, and he gets the equation that delta x equals delta x prime divided by beta. So he's saying that when I measure in the rest frame, my distance as defined in the moving frame is contracted by the factor beta. And then he makes the statement, the body's kinematic shape. He's introduced a new terminology in his 1907 paper. He talks about kinematic shape. Differs from its geometric shape. Boy, he's really put in a mouthful here. By a contraction in the direction of the relative motion in the ratio of 1 to 1 over beta. I don't know if you know what he means. I don't. So it's not clear why the correct conclusion is not dilation again, according to our x prime equals beta x. Now, I think that's the correct solution. So he should have come up with dilation. Okay, but what he does is he essentially fudges the math. You heard of that term, fudging the math? Okay, he basically fudges the math to get the answer that he wants. he says, well, my theory has to agree with length contraction because Lorentz claimed length contraction and Fitzgerald proposed length contraction to explain the Michelson-Morley experiment. So what I'm going to do is I'm going to fudge around with my math so that I could get the length contraction equation out of my math. Okay. In 1910, now remember, these are different papers, and he's you can't really say he's so much changing his mind so much. He's kind of coming to the same conclusion, 1905, 1907. In all these papers, he's reaching the same conclusion, but he's using different arguments. Okay, and that's kind of what causes some of the confusion. Okay, so in 1910, he also doesn't tell us that he's setting the evaluation condition T prime equals 0. So again, he's defining distance in the moving frame and using the Lorentz transformation for T equals 0. And he says, at any distance T of the system S, we will have the following between coordinates. And then he gives this equation, delta x equals delta x prime divided by beta. And, that sort of appears out of midair. He's kind of like assuming that you, the reader, knows what he's talking about and is going to believe him because, he said so. And then this is the real reason for talking about this. It's the first time he says this. He says, one recognizes at once in these equations the hypothesis of Messrs. Lorentz and Fitzgerald. Here, this hypothesis appears naturally as an immediate consequences of the principles assumed. So in his paper in 1910, he says, oh, yeah, look at this. I get the same, my answer in my theory gives Lorentz contraction just as postulated by Lorentz and Fitzgerald and these other guys. And so therefore, my theory is consistent with their theory. And yay, my theory works. Okay. Then we have Einstein's 1911 paper. Now, this is kind of, he doesn't, this is kind of not as mathematical, and it's more of a philosophical discussion. So he says, if we have a body that is moving uniformly with respect to K, then this body appears contracted compared to its shape at rest. So he's saying when a body is moving and we compare it from the rest frame, we see that it appears to be contracted. It's not really clear exactly what he means here. Okay, then he said, this is kind of the thing that Jerry mentioned earlier, says, when its velocity reaches the velocity of light, it will collapse to a plane. So he said, we have a rigid body traveling near the speed of light. It's going to collapse into a plane. However, as judged by a co-moving observer, the body retains before and after its shape. Wait a minute. He says, well, it collapsed to a plane when it was moving at the speed of light, but now he's saying that if I'm moving with the object, nothing happened to it at all. Okay. This is justified because this shape can be ascertained only with the aid of determination of time. So his explanation is that this has something to do with time. So since time is changed by motion, so is length, but in a different way using different definitions. So yeah, now length contraction is really basically how are we measuring time? That's kind of what he's saying. It's kind of obscure. Okay, now I want to mention here, this is Landau and Lifshitz. You probably heard of them, Vladimir? That's a famous Russian.
They were great physicists.
Right.
And there are a lot of textbooks by their names. Yes, yes. I knew that.
Yes. This comes from the classical theory of fields. They have a whole series of textbooks on physics. Okay, and so their procedure is they use the inverse transformation solve for t prime equals 0. So they're solving the Lorentz transformation under the evaluation condition t prime equals 0. So it's evaluation in the moving frame. And then they obtain x equals beta x prime. And then they do kind of Einstein's favorite trick. They reverse it and get length contraction. So they invert so they solve the, and by the way, this is a coordinate transformation, x equals beta x prime. That's a coordinate transformation. Then they invert that and get x prime equals beta x. And that's the Lorentz contraction formula. Now, kind of the reason I brought this up is because, in effect, basically, they really haven't changed what Einstein was doing. I know that Roger Anderton keeps saying, well, they've changed the theory. Well, yes, but did they actually change the predictions, the equations that they're using? No, they're pretty much staying the same. All right. And, okay. Now, one of the things that's interesting is that you can, in reverse this equation, you can take the x prime and take the prime away and make it x, and take the x and put a prime to it, and that's the doing the symmetry. Einstein says by symmetry we can do this. And then, so what we'll do is we get the length contraction law in the opposite or the other frame. Okay, so we have these symmetrical equations, delta x equals delta x divided by beta, and then we can have the symmetrical equation delta x equals delta x prime divided by beta. Okay, and so you get these symmetrical equations. And so that means that length contraction is symmetrical. But if we do this, we have this problem that we get a paradox. We get paradoxes. Okay, this is how you get these paradoxes in special relativity relating to measurements that involve length. And there's a number of these paradoxes that are out there. And so the only way we can get rid of this paradox, these paradoxes that we have, is to say that the solutions that you get when you do evaluation using the Lorentz transform, the symbols are not the same as the symbols that are used in the inverse Lorentz transform. So they're actually different. They're saying different things mathematically. Okay. And that's the only way we can really escape these paradoxes. We can't really assign the same meaning to the Lorentz transformation and the inverse Lorentz transformation. My solution to this difficulty is to assign the fact that they're doing the basis transformation and the coordinate transformation. Those are the two things that you need to do to have a measurement. You need to have a measure unit or a basis unit, and you need to have a coordinate number that describes how many of the basis units are in a measurement. Okay. And so here are the symbols used in the Lorentz transformation and the inverse transformation have different meanings. And I claim that the inverse Lorentz transformation is a dual transformation. Corresponds to a transformation of the dual space, which is a complicated mathematical concept. Okay, and so they're dual. The symbols used in the two transformations are dual. And what dual means is kind of difficult to explain. It's not the same thing as being reciprocal. What happens is that they're inversely related, but the directions are also reversed. That's kind of hard to understand. So I'm not going to go into that too much here because it's confusing. All right. Okay, so what does this mean physically? The different equations relate the units of scale, length, and the counts of unit length measurements. I've made this point over and over and over again. Okay, you have to have the two things in a measurement. You have to have the unit size, and you have to have the number of units that you count. Those are transformed differently by the Lorentz transformation and by the inverse Lorentz transformation. And we have to take both of those into account in order to make a measurement. Okay. All right. And special relativity, there's no, this is kind of confusing to say. One of the things that's interesting is that length contraction uses basis transformations and time transformation uses coordinate transformation. So the time and distance are not based on the same concepts in special relativity. And so because the time is, the equations he uses for distance, he talks about Lorentz contraction. And then when he talks about time, it's time dilation. These two ideas really just don't go together. That's the bottom line there. All right. Okay, so in effect, basically, there's actually no Lorentz, there's no contraction. Okay, what the contraction that we think they see is really the fact that the units that when we make a measurement in the rest frame and then we talk about the same measurement in the rest frame. So if we define a unit of length as 1 in the moving frame, the basis transformation says that the units are smaller in the rest frame. So it looks like going from the moving frame to the rest frame, that an object that is measured in terms of units has gotten smaller. But that's not really the case because we didn't take into account that the units are not the same size. The measure units are not the same size. So that's why I call it the length contraction mistake. There's not actually any contraction taking place. It's a mathematical mistake or a artifact of the mathematics that's being used. And in case of Einstein, he assumes always, and I brought this up in the beginning, he always assumes that there's no change in the measure units. He only assumes there's a change in the coordinate system, at least for time. But he gets it all mixed up. So you really can't make a definitive statement about what Einstein did or said, because in one case he did one way, in another case he did it another way. And that's where you get into all this confusion and argument about what is special relativity, what it means, how do you interpret what it means. It's just a lot of different stuff, bad mathematics kind of mashed together into something that's supposed to make sense. Okay, I'm not going to go into and here's another example of what I've been talking about, mixing up these concepts. Go ahead. Okay, there's what's called the lever paradox. Okay, I don't know if you're familiar with the lever paradox, but this is another example where there's a paradox that's created by the confusion about time dilation and length contraction. Okay, and it turns out that if you use, and this goes to Hasio by I that I talked about before, where he solves the lever paradox. But the way he solves it is he uses consistent evaluation conditions. So in other words, if you're evaluating time, you evaluate time, you do it the same way that you do distance. In other words, if you solve for the evaluation condition, say x equals 0, setting x equals 0 in the rest frame, you set t equals 0 in the rest frame. And you use the equations that you get under those two consistent conditions. And if you do that, you don't get any paradoxes, according to Hasio by I, as far as, and this is another problem where all these paradoxes come from, because the paradoxes arise from misusing the equations and not doing the evaluation correctly, not identifying that this is a basis change law or a coordinate change law. He just mixes them all up together. All right, so here's my summary. There is no length contraction. It is an Einstein math error due to a misunderstanding of how measurement is done, compounded with math. Okay. It is incorrect to say in relativity that a distance is contracted or that a time is dilated due to motion. Okay, that's because not taking into account that there is a measure unit and a number of measure units in a measurement. Einstein basically doesn't take into account those two different things. He only sees that the what he thinks are coordinate transformations. He only sees that the coordinates have changed. And because he sees the coordinates have changed, he says that length has contracted or that time has dilated. But if we take into account the fact that the measure units change and that the number of units counted in the measurement change, when we look at they change reciprocally, and we take into account both of the transformations, we find out there's really no change in time or distance. And so then time and distance is invariant. What changes are the units of measurement and the numbers that are counted in the measurements are different. Einstein implicitly assumes the units are the same, don't change to measure units. Einstein, when he's talking about time, well, he doesn't really acknowledge that the units change at all. The units for Einstein are always the same. The rulers are always the same, and the clocks are always the same. Okay.
So now it sounds like you're saying that the muon Lorentz transform to explain muons at the Earth's surface is a misapplication or is irrelevant.
Well, actually, his theory doesn't apply to that at all. That's why it's kind of a mess, because he doesn't have he tries to. It's complicated to explain, but it's just everything that Einstein does is a mathematical mess. That's the main thing that you ought to understand. It's just a mathematical mess. The concepts are mixed up. They're not really clearly defined. Measurement is not done clearly. It's just a mess. And to say that Lorentz transformations are invalid is not really correct. Yeah, in Einstein's theory, they're not used properly, and because his mathematics is a mess. He's not a very good mathematician. Now, what happened was Minkowski came along and tried to clean up the mess. Maybe, I don't know whether Minkowski was trying to clean up the mess. I guess he came up with an alternative idea. He had a different mathematical explanation of what was happening. But his explanation really basically conforms to what Einstein said. So if you use Minkowski's space-time, you still have length contraction and you still have time dilation. But if you go into the details of it, the way they explain it with these peculiar geometric diagrams, it's pretty obvious that they fudge their proofs and their demonstrations to get the result that Einstein got. And the result that Einstein got looks like he fudged the math to get those results as well. So it looks like Einstein came up with time dilation probably because Lamore had calculated a time dilation in his theory. That's kind of a guess on my part. There's no real proof that he did that. He could have just as easily got time contraction. You know, he could have. His method is basically he's fudging the math to get the result that he wants. And it looks like in the case of time dilation that he may have looked at some of the results. There were results that showed that spectral lines on the sun were redshifted. Maybe that was he used that as part of his theory to explain it. So in the case of length contraction, it's a little clearer. He pretty much made his theory agree with what Lorentz and Fitzgerald had come up with. They claimed there was length contraction. And so it's pretty clear he fudged his theory to get that result.
So if time and distance is invariant and don't change, why would we need a Lorentz transform in any situation?
Well, because they use it in, Jim, I suggest you read some books on physics. Maybe reading.
So in other words, that's a non-answer. You cannot answer the question. Thank you.
Well, that's a cheat on your part for saying that. You're asking questions that really aren't legitimate questions that I can answer.
Well, now that's a correct answer. There's nothing wrong with saying I cannot answer a question.
Well, I suggested to you that you look at some physics books where Lorentz transformation is used in physics.
Well,
okay.
I've read hundreds of physics books on particle physics for your information.
Well, apparently you didn't understand that they're using Lorentz transformations. Did you not understand that Lorentz transformations are used in? I mean, just go.
Well, what either of us understand or don't understand.
Go and type in experimental test of special relativity, and they'll tell you about it.
I would prefer to talk about science and not what we understand or don't understand.
Particle accelerators, okay? It's used thousands of times a day in particle accelerators. There's thousands and thousands of tests of special relativity according to them. Okay, haven't you read any of that?
Well, that's what you claim.
I'm not. Just go on the internet and look it up. I mean, you're making this into a credibility dispute between me and you.
No, it's just a discussion.
I mean, why don't you?
You're a very credible, outstanding person.
Just go to AI.
Ad hominems have no place in these discussions. That's all.
Well, you started it off. You basically started it with your questions. Your questions. Every question that you've asked is essentially an attempt to create an ad hominem situation here, putting me on the spot, asking me questions about something that I don't advocate. It had nothing to do with my presentation.
Well, that's not my motive. I deeply respect your work and your presentations, and whether or not you agree or disagree with Lorentz transformations, what I've done here is I've explained a number of the mistakes and how to correct the mistakes that are in the existing theory. Okay, you don't necessarily have to believe in Lorentz transformations. You might want to believe that these mistakes are probably legitimate arguments for the things that need to be corrected. Once they're corrected, then you can apply the theory, the correct mathematical theory, to the experimental results, and then maybe we can get a better understanding. Actually, I think it's outstanding, Harry, that you summarize and conclude that time and distance are invariant. I think you've done a wonderful job in presenting that, and I certainly don't intend any slight to you as a person, and definitely not as an intellect. You're an outstanding intellect by anybody's account. Thank you.
I like this conclusion of Jim about the absolute time and space. It's very important conclusion. It's good. Let me tell you my understanding what you reported today.
You're going to get cut off there.
It is, I'm sorry. It is not mistakes in math. Math don't blame.
Okay, you were saying, Vladimir.
Let me continue. It's not math in mathematics. Don't blame it. It's okay. The math is logic. There is no logic because you are playing with the same formula, with the same parameter, beta, gamma, it doesn't matter how to name it, but logic. There is no logic. And the second point, Somebody genius, Einstein, he claimed it must be this and that. And then all this mess in logic is directed to how to prove, how to confirm his claim. You see, he tried in different papers to, to confirm, to prove his claims. But claims from where? From sky, from cosmos, from where? That's why, it's not the right way to even to tell math in mathematics. No, math in logic. And logic, it's look directed to how to prove, and that's it. All the other guys, they're doing only for this person, for this goal, for this aim. I do like your experimental approach to different space, to different space frames, whatever. You know why? Because I'm experimentalist. I cannot tell anything about the moving system because I am not inside of it. I don't have these experimental tools how to measure these parameters. You see, we can measure our parameters only in system we are. And if you are moving with your system, please measure your system in basic units of this system. That's why this is the main goal and the main objective of your presentation. And I like it very much because, it's experimental proof. It's not theoretical. In a S system, I cannot measure anything in S prime system. I cannot. I have to go to S prime and then to go. The second very important point, there is a claim, and it's a very good claim. If your moving system goes with the same speed, the same velocity, laws of physics must be the same. But laws in physics measured in the same system, not in your system. You see, there is a conflict of these even claims. You have your physics the same, but you're talking about the physics in one system based on your sitting in another system. It's conflict, it's contradiction. Simple like this. The next very important point, let me tell you about this, my understanding of special relativity. It's a wasted time, because there is in our world absolute frame of reference, cosmic medium. There is absolute time that is exactly the same in all the points of our system. What is it more important? Our physical laws depends on parameters of cosmic medium. If we have cosmic medium in one space, in one frame, then please count on these physical laws. If you're going to some other system, please start from everything from the beginning. Your physical laws depends on what? It will be different cosmic medium, or it will be different, I don't know what, ether, whatever. That's why conflict of interest is that you are trying to measure some physical laws in a different systems, and you don't know how to measure it in a moving system at all. That's why the main advantage of your presentation for me, please stay with the same system. You are in the system, measure your parameters and everything in your system. And don't ask even the question, what you will get from the other system. You are not. You are observer only in your own system. You cannot ask even this question. That's why all these contradictions with time dilation, with space dilation, it doesn't mean at all. It's against logic. Sorry for my emotions as usually, but as I told you, it's a wasted time. I want to ask one question of Roger Anderton. He is an expert in this business, special relativity. Did he ask artificial intelligence about this math and mathematics? Did he ask you, Roger? Because you're talking about this special relativity. For me, it's a wasted time and money, whatever, because there is no meaning for this theory at all. There is no logic from the basic points, from the logic, from philosophy. Simple like this. That's why let's stop talking about this issue, because we are wasting time. We are checking our own logic. In different logic, you have a different conclusion. But what is important? All other scientists, they followed genius Einstein. Einstein claimed it should be this parameter, should be this effect. They're measuring their logic, math logic, it's exactly directed how to prove his claim. You see, it's
All
many
right.
times I told you
All
guys,
right.
I said, let's stop talking about special relativity at all, because there is no meaning for it. It's mathematical tricks, mathematical math to prove somebody's claim. We don't know where it came from. Sorry.
Well, that summarizes kind of what I've been trying to say. But my point is, I think there's some ways we can clean up the confusion.
Need
And
to do it. You done already, sir. I ask you. You done two good presentations. And if it's not correct math, what we talking about? Because physics based on wrong mathematics, wrong logic, it's not physics. Let me remind you that physics is experimental science. If you're talking about velocity, please tell me how you measure it. And the same story with all these contractions and dilations and so on and so on. That's why the main value of your two presentations is very simple. Guys, stay physicists, experimentalists. Tell me if you told something, tell me how you measured it, how you prove it. Simple like this.
okay.
Not mathematics.
Question.
They're not.
Just about your principle of using the basic and coordinate measurements. You've applied this to time and you've applied it to length, but you don't seem to have applied it to mass. Do you do that, Harry? Mass
Well,
increase with velocity.
that's an interesting question. I'm working on that problem. It turns out that it might not be that mass changes. It may be that acceleration is where the problem lies. So, in other words, if you do, to me, it looks like what happens is that mass looks like it's increased because if in the rest frame we apply a lot of units of acceleration, according to our ideas of physics, in other words, we have an electric field that we measure, and we say that electric field ought to apply X units of acceleration to a particle. Well, it turns out if you look at it from the rest frame point of view, you need more units, okay, of force to get a single unit of acceleration. So in other words, the acceleration that you get is diluted and the faster you go. Does that make sense to you?
Well, sort of. I mean, I'm thinking along similar lines myself because it appears that from the particle accelerators, that's the way they normally explain the results and the geometry of the circuits they get and so on. But it may not be mass increase. It may be something along the lines you've been measuring, acceleration, or even a force. But
Well,
because
my
I do
thesis,
basically also agree with the negation of time dilation and length
right.
contraction.
My theory about this is that because a 1 unit of measure in the moving frame corresponds to many more units of measure in the rest frame. What that means is you have to apply a lot of units of acceleration in the rest frame to get a smaller unit of result in the moving frame.
Okay, I have a comment. Let me have a comment. First of all, there is no mass of particles. There is no such definition. Mass is a classical notion. That's why for particles, we can talk about rest energy only. There is no mass. There is no mass, guys. The very first point. The second time we're talking about one photon, one electron, one quantum object. How do we know the speed of it? How? Because if you want to measure speed, you must have your measurement of your space or measurement in length and measurement in time. But time and length doesn't exist for quantum physics. Doesn't exist even. That's why even to talk about the speed or velocity of your particle, I don't know what you're talking about. How you measure it? Guys, I am
Well,
experimentalist. If I have some
as we
parameters,
discussed
I want to
earlier,
know how you measure it, and even increase of the mass.
hold on. It's done circularly because the theory tells them what this velocity is because of the energy that they calculate. So in other words, it's kind of, as you say, it's kind of circular reasoning, but they basically accelerate the particle to a certain energy level in the accelerator. And
Increase
then
energy, and that's it, guys. There is no mass.
According to their theory, that a particle which has a certain amount of energy, their energy that they calculate, has a velocity that they can calculate based on their Lorentz transform formulas. So it's kind of circular in that there's really no independent measurement of velocity. It's all based on.
Yes, it's exactly. But it is impossible. Remember, you cannot measure at the same time position and speed at the same time. That's why how to go against the quantum physics, the main point. In different, there is no exactly the same points, the same measurements for velocity and space. How to measure it? That's why all our classical notions we cannot apply to quantum physics. We cannot. It doesn't work for us.
Well, yeah, we're sort of in the netherland between quantum physics and classical physics and special relativity.
It's exactly my point. Special relativity, that's the mathematical tricks, and that's it. There is no physics behind special relativity. And there is not some different level or different physics. There is a concrete wall between quantum physics and classical physics. Quantum physics, it's single objects. Please play with them without space, time, and all this mass and all this parameter of classical physics. 100 years ago, classical physicists, they started to develop quantum physics. That's why they didn't have anything at that time. I'm not blaming them, Bohr and all the guys, Dirac, because they didn't have anything in their hands. After 100 years, at last we must put our questions. What is the difference? Quantum physics and classical physics. Many times I told you, quantum physics is separate physics. Separate, it's not classical. Classical, it's ensemble of these particles. Simple like this. You cannot transfer your laws for ensemble of particles to one particle. It's forbidden. It's a different story. That's why, guys, special relativity, it's a wasted time. It's a damaged logic, damaged mathematics. We are wasting our time because of you. You proved right now mathematically what is the mess in their logic. And logic, it's only one direction. How to prove, how to confirm these, claimed effects. Twin paradox, like contraction time, delay, so on. But they don't even exist as parameters for quantum physics. There is no such parameters because as an experimentalist, if you're talking about something, give me the way how you measure it. And we can measure only classical parameters only. We cannot tell anything about the quantum parameters, quantum physics parameters.
Okay.
Oh my goodness. I'm tired already to talk about the same story. We're already 100 years later. We have so much now to see around us, to see the classical physics, this achievements in astronomy, cosmology, and all this stuff. And why we're talking about quantum physics at the same time, I don't know.
No. All right.
I told even, for quantum physics, even Jim approach, it works for me because he has totally different story. There is no space, there is no time. There are some objects and he plays with this object. And it is his way how to play. Jim, play, continue. For quantum physics, it works many times, I told you right now, because for quantum physics, you can play with any equations, with any mathematics, with any computer. And I want to ask Roger, do your artificial intelligence know about the Harry Ricker, about this mathematical mess, about everything? Because you refer to this IE, AI, oh, sorry, AI, and you never told us about this mess. How come? Harry, he convinced me 100%. Math in logic, math in mathematics. What about your artificial intelligence? Does he know about this or not? And why we should continue even to waste our time with this? Let's find some other experimental phenomena, very important right now, very, with unexplained and so on and so on.
Right.
We will go with classical physics and we will continue to grow up as a
Let him
physicist.
answer your question.
Yes, sir.
Can't hear you.
Yes.
You're muted.
I'm sorry?
You're muted.
No,
You're
I'm
muted,
not.
Roger.
Roger is muted.
Roger muted. Why?
Roger, you're muted.
I don't know. Oh.
Roger, unmute yourself. All right, can't hear Roger. Okay.
Mind you, sorry, but anybody can plug in that question into AI or ChatGPT. I think Roger would be the first to say that he's merely doing what anybody could do. The tools are available. So try it yourself, Vladimir. See what happens.
I'm not expert in special relativity. I told my opinion. It's a wasted time. I have so much to do in my life with classical physics. For me, there is no meaning at all. I'm sorry. If
No,
I
I'm just
didn't
saying,
convince you,
I hardly waste my time looking at these things.
Okay, Roger, are you still
waste my
muted?
time on it. There is no meaning for it.
No, you're still muted.
I am muted or who?
Roger's muted.
Roger muted. Because, I asked him this question because, for me, it's convincing. You've done a great job, Harry. Thank you so much. I'm not expert in this business, but the most important point you told me, you must use the basic unit for each frame, for each space, whatever. If you are in this system, take your measurement system here. If you're going to the other system, measurements should be different. It should be accordingly done.
If I may be bold enough just to guess what Roger might say, because those of you who saw his lecture yesterday will perhaps concur with this. He saw a difference between ChatGPT and the other one, Gemini. So I imagine that ChatGPT would probably concur that there is a mess in the analysis of Einstein and in the normal analysis of Lorentz transformations and so on. And Gemini would probably come in and say, no, what you're talking about is nonsense. You don't understand it. That's the import of, I think, what he was saying yesterday.
Hello, can you hear me?
Gotcha now. You're real loud, though.
Sorry. Yeah, I don't know what's happening. My phone. So I use artificial intelligence, AI, because you can't really talk to these experts, the elite, on special relativity. And I'm hoping that AI gives you an insight into what these experts think about things. And so according to the AI, both AIs, ChatGPT and Gemini, what happens is they do correct the mathematics in special relativity, and then they apply it to experiments, and then that works. And so they say special relativity works, but the corrections they make are implicit, which is another word of saying they're not telling you what corrections they're making to special relativity when they're doing this. So from that point of view, yes, the physics of the theory works. The theory works, physics is okay, and the metaphysics is then a mess. So the metaphysics of special relativity is a total mess, and Gemini says metaphysics is unimportant. It's just the physics that's important. And so they're saying, yes, so theory, special relativity is correct, is a correct theory. But ChatGPT is open to the possibility that when a theory's metaphysics is a mess, then the theory is wrong. So it's a question of how the two things have been programmed. One is willing to accept metaphysics as a reason for a theory to be wrong, and the other one is not willing to accept that. And that's the situation. The elite, the so-say brainy ones, like Professor Hawkins and that, they've made all their implicit corrections to special relativity, and then they say the theory works. And that's the state of physics that we've got at the moment. That's only for, so say, the elite that know what's really going on.
In my prior comments about Harry's conclusion, I find it that we should really applaud his conclusion where on that last slide it states that time and length are invariant and actually don't change. And may I perhaps invite Harry to elaborate a little bit? It seems like that conclusion just popped up, and maybe to help some of us understand how the foregoing math analysis led him to that very interesting statements.
Well, I've talked about this before, and
that time and length are invariant?
Yeah, I talked about that in the first talk.
Okay, well, I think I just
missed it. All right, well, here's...
I heard all of your talks.
You see this?
Yes.
Appendix mathematical proof, it says. The Lorentz transformation is derived from a... Okay, so this is a very complicated way of... This kind of gets into the deep. The Lorentz transformation is essentially the starting point is a quadratic form. And a quadratic form has what they call a dual space solution to the set of solutions. So you have a set of solutions and you have a dual space solution, set of solutions. What the dual space is, and they're related reciprocally by an invariance principle. Okay, and so the dual space is, so if you take the anyway, it's kind of hard to explain it. You know, I'd have to go into a lot of mathematics, but anyway, so the quadratic form is a square. So here, this is one way of explaining it. Okay, so the solutions admit of two systems of solutions. Okay, what are the two systems? Okay, I've given them a name: basis solutions and coordinate solutions. Okay, and they're dual to each other. The coordinate solutions I believe to be in the dual space according to my definitions. Okay, if we multiply the basis and coordinate transformation equations, so we get, so here's a basis equation, x prime b, call that the basis equation, and then we multiply that with the coordinate equation, we get essentially the square x squared, I did this wrong. Anyway, what it boils down to is that the beta in the top, you see, when you multiply, you got x prime divided by beta times x times beta. The beta disappears and you get x squared, x prime squared, which take the square root and you're going to get 1, okay? Because that's kind of a flaky way of explaining it. Here's we'd look at it another way. Take the time equation, t prime equals beta t, and then we have t equals beta t prime. Okay, one is the equation for the basis and the other is the equation for the coordinate. That when you multiply them together, the betas go out because it's equal to 1. So what this says is that the coordinates get that because of the difference between the units in the rest frame and the units in the moving frame are different. There are fewer units counted in the moving frame than in the rest frame. and vice versa. There are more units counted in the rest frame than are counted in the moving frame. And so what happens is when you multiply the length of the basis unit times the number of units counted, whether you measure it in the rest frame or the moving frame, you get the same result.
Okay, I think that helps clarify how you got to the conclusion of the invariance of time and length. Thank you.
Does anybody have any questions about that?
Well, I have just an offhanded question. Uh, does anyone else agree with the idea that only the units of measurement transform? Or I mean, because I know you spent a lot of time and effort developing a theory, which is quite impressive. I just didn't know if it's. I mean, because I looked it up once on ChatGPT and they couldn't find anyone who thought that. So I just didn't know if you knew of any other people.
Well, I discussed this in the first talk that I gave. This isn't an idea that I came up with. I borrowed this idea from Sachs and Harada, and who published a paper on this and physics essay. They did a couple of papers, and they just proposed this as an idea, and of course didn't go anywhere. Also, Dingle in the 1930s, he proposed basically. He had a different take on relativity, and he had the idea that time when we were talking about time and special relativity, that it had to be talked about in terms of the standard definition of a measure unit of time. Okay, and so the idea isn't necessarily mine. I borrowed it.
Okay. Well, I have to admit, I mean, I've always heard that the Lorentz transformations were designed to account for the invariance of C. And if you don't accept the invariance of C, I don't understand how it could work. I mean, is there any way you could describe it in plain words?
What do you mean? Well, it turns out, I'm not sure what you mean. It turns out there are two ways to think of the Lorentz transform. You can think of the Lorentz transform as being that C is the same in both the rest frame and the moving frame in terms of the same units of measure. Or you could think of it as the velocity is C in different units of measure. So you change the units of measure in the moving frame to make it so that the result is C, but in different units. I explain that in my papers. Does that help you any?
Yeah. I I have questions. It's just, I mean, if the units of measurement transform, and I know I've asked this before, I mean, why wouldn't objects outgrow the units? I mean, do the objects shrink with them to make it consistent?
No. Essentially, what it boils down to is when you're talking about the laws of physics, you need to have a measurement. Okay, so in other words, the laws of physics deal with something that's measured. Okay, normally when you put numbers into laws of physics, you don't put units into the laws of physics. You just assume the units are the same. Okay, so what happens is that what looks like to be the case is that the units are different. And so the units in the rest frame are not the same as the units in the moving frame. But the laws of physics remain the same in the transformed units. So does that help you any?
Well, would you say you accept emission theory, like that velocities add?
Well, we're not talking about that. We're talking about.
Well, I mean, it's relevant though, because I mean, if velocities add that way, if light isn't invariant, it would seem that Galilean transformations would preside.
All right. Well, I'm glad you mentioned Galilean transformations because I have a little talk here on Galilean transformations if you want to hear it.
Sure.
You see, it seems to me in a way, you're still on, yeah, I thought we're ending. That there's a major problem there which you've endeavored to resolve. But I don't introduce the problem because I reject these transformations, as you know, and I start with Galilean transformations. Now, I have some other means to look at the physics, namely total derivatives, which make Galilean transformations, or so I claim, the correct transformations for
Well,
kinematics.
turns out the scale change interpretation of, okay, so it turns out that when you use this scale change approach, turns out the Galilean transformations apply. Turns out that in this theory, the velocity is invariant. So that means that there's the Galilean velocity law. So we have the Galilean relativity law, if you will, u equals u plus u prime, where u is the velocity relative to a fixed frame, say s. So in other words, we've got a velocity v relative to a frame that's moving with velocity u prime. Okay, now v is the velocity of the moving frame s prime relative to the rest frame s. And I talked about that. U prime is a velocity relative to the frame s prime. Hence, u is the total velocity relative to the frame s. Okay? And then Einstein has this velocity law. U equals u plus v prime divided by u plus uv divided by c squared. Okay. This thing. You're familiar with this thing? The velocity.
Yes.
This is Einstein's velocity addition, the relativistic composition law for velocities. And if you start using this when you're doing momentum calculations, you get all these complicated expressions. All right. Using the scale change laws recovers the Galilean transformation law. Well, what happens is that we can go through the math and we can substitute the transformations x prime equals beta x and t prime equals beta t. Okay, the first thing that you're going to realize is that because the x prime and the t, this basis change laws, they're in the same form, right? They're consistent, they're congruent with each other. So if I'm going to divide x prime by t prime, I'm going to get beta x divided by t. And then that means if these x represents changes as in velocity, the velocity doesn't change. So the betas divide each other and come out to be 1. Okay, so the relative velocity. So what happens is that the velocity of the frames relative to each other. So in other words, the velocity of the frame s relative to s prime. Turns out that velocity is the same in both frames. There's no change in velocity. Okay, so if we do the calculation, delta in velocity v and the rest frame, delta x divided by delta t, now we're going to transform it into the moving frame. We get delta beta x divided by delta beta t, and that's equal to delta x prime divided by delta t prime equals v prime. So in other words, when we do this transformation, it doesn't change the velocity.
So you're recovering the basic laws that come out of Galilean transformation, namely constancy of length, constancy of time, and indeed the velocity addition law. And by the way, Jerry said, "Oh, do you mean emission? So you should have said a ballistic. It's a sort of a ballistic thing with addition." Yeah.
Okay. Well, then I have this complicated mathematical thing here where I go through the proof and I show, basically that his velocity addition law, Einstein's velocity addition law, isn't needed. We can, if we do the measurements of velocity with the scales changed between the two frames, turns out that the Galilean law we get the Galilean law, the Galilean addition law, because velocities transform invariantly, which kind of is essentially what we did when we created the Lorentz transform. We created the Lorentz transform to essentially the velocity is the same in the moving frame as it is in the rest frame. And we came up with changes of variables that made the velocity and the moving frame the same as the velocity in the rest frame by this Lorentz transform. That's what the Lorentz transform does. So the velocities are unchanged. Okay, and you say, well, how come special relativity didn't discover this? Well, because he messed up his length contraction and time dilation equations. So he's got length contraction and time dilation. Well, length contraction and time dilation don't make the velocity in the moving frame the same as the velocity in the rest frame. Now, good friend or good buddy Stephen Gift has turned this fact into a virtue of the Solari transformations. So they turned this mistake in Einstein's theory into a virtue in the Solari transformations. I find that amusing. Okay. Does this help you any, Jerry?
Well, I'm not very well versed in math, of course. I mean, I have a question though, as far as the invariance of C. I mean, if C isn't, I mean, like as far as how where is C invariant? I mean, where there's relative motion of objects involved.
It's not really it's a trick. It's a math trick. You understand that? It's a math.
So it doesn't occur in reality.
It's kind of hard to say that as a blanket statement. What do you mean by it doesn't occur in reality? The theory, I mean, this is basically the Lorentz theory. The Lorentz theory says that the speed of light is c only in the rest frame. But what we do is for the moving frame, we change the units of measure.
Yes.
The scale units in the moving frame. And when we do that, the velocity measures in the moving frame. The velocity, the measure of c is the same as in the rest frame. So
It
we
must be.
so c is not really invariant in the moving frame. It just appears so because we changed the scales.
So once you change the scales, that accounts for the discrepancy and things even out.
Yeah, you can think about it that way. But what happens is when we do this is that now it turns out the usefulness of this theory is that it allows us to use our laws of physics that are valid in the rest frame in a moving frame.
Yeah. Which it's
Point. Yeah, you're absolutely right, Harry. You're absolutely right. Harry, let me ask question Ian about the future Saturday session about the collapse in gravitation in general relativity. If it will be the same guy, if I understood correct, how we can proceed with him? Because then last time he didn't understand even one word in English. It will be translator. It will be something. He put so many equations without any reason. That's why, I was very interested in his approach to this collapse, but I didn't understand anything from his first presentation, and now will be the second the same. It's a wasted time. I'm sorry.
Well, thank you for raising it. I've had to look at this, and actually, it appears that it's probably his hearing. He's very poor hearing. He writes very well. He seems to have a command of English pretty well, and he doesn't understand some things. But he had his son beside him at the last lecture, and his son, I think, probably doesn't speak English. He wasn't there for that purpose. But at the next lecture, he's going to have a man who will act as interpreter. So if we don't understand, if he doesn't understand me or I don't understand him, the other man will work out. Now, the other thing I would say, Vladimir, and to all of you, is his